Well, thanks a lot for the opportunity to give this talk and to participate in this very nice workshop. So indeed, my talk is going to be on six-dimensional superconformal field theories, and I will be interested in understanding how one can define and compute partition functions of these theories on a space-time, which has a factor which is an ALE space. So in particular, I will be interested in the simplest possible case, which is C2 modded out by Zn. So 6D theory requires an extra 2 dimensions, which I will take to be a torus. and throughout the talk, I will denote the complex parameter of the torus by tau, and as should be already obvious from where I'm going, the connection to the theme of the workshop will be modularity. So the goal is to understand the properties of class of six-dimensional theories, which have chiral supersymmetry, in particular, one left-moving supersymmetry corresponding to 8 supercharges. And I will take these theories to be, well, superconformal theories, but deformed to be on what's called the tensor branch. Which is very much similar to the type of setup that was considered in Kim Young's talk earlier in the workshop. This is also the first beginning work on this topic, so I will also choose the simplest possible type of six-dimensional theory. So for this, I will take the gauge algebra associated to the 6D theory to be just a unitary group. UW, or more generally, a product of R minus 1 copies of UW, where R is also the number of tensor multiplets in the theory. So in the end, one is interested in computing some partition functions which count BPS objects, and it will turn out that the partition function will take a familiar structure, which also arises in other computations, such as Nekrasov partition function in 5 or 4 dimensions. So it will take the form of a perturbative contribution multiplying an instanton part. And what's characteristic of six-dimensional theories is that that instantons, the instantons with respect to this 6D gauge algebra, are strings. They're two-dimensional extended objects which one can wrap on the torus, and they couple to the two form fields in the tensor multiplet via an interaction of this form on the world sheet. And actually, one can see that they're instantons because of the existence of a term in the 6D spacetime, in the 6D action of the form B wedge trace of F wedge F. So a field configuration which has a non-trivial profile of F wedge F is a source of B field on the remaining two directions, which here I take to be the torus. Okay, and now there's been a lot of work on understanding partition functions of this type of setup of this type of theory on the background T2 times C2 for many different classes of six-dimensional theories. And now the goal is to see what happens if one tries to put these theories on more complicated backgrounds with non-trivial topology. And the upshot will be that many aspects of the story are similar to what happens on T2 times C2, but there's a new aspect, which is that the strings they interact non-trivially with some new type of degrees of freedom, which are localized on the torus and are a collection of chiral fermions. that will be responsible for interesting type of modular behavior of the partition function. And there will also be responsible for the fact that the worldsheet theory that describes these instanton strings, rather than being a ordinary quantum field theory, will be a relative quantum field theory, which doesn't possess a well-defined partition function, but rather possesses a vector of conformal blocks that depend on some additional data. Okay, so the motivation for this work is, first of all, to learn how to compute observables. Of six-dimensional theories. And being intrinsically non-Lagrangian, these six-dimensional theories cannot be studied directly using localization, and one needs to come up with other ways to study them. And one way is to study their solitonic degrees of freedom, such as the instanton strings. And that's the approach that I will pursue. In particular, the interest is in understanding what happens with if there is non-trivial topology. So for this class of superconformal theories in 6D that I discussed today, I will be able to actually completely understand the QFT that describes the strings, two-dimensional QFT. But more generally, one can't, one shouldn't really hope to be able to have an exact understanding of these theories. They're generically strongly coupled. And what becomes important then is to really understand in detail what are the modular properties of the partition functions of these strings or elliptic genera, which then end up contributing to the 6D partition function. Because knowing the modular properties is often gives enough information to completely determine the partition functions, even if it's not possible to have a complete description of the theory on the strings. And maybe another important reason for looking at this kind of setup is that is because of geometric engineering. Which relates the six-dimensional theory to an elliptic, non-compact Calabi-Yau threefold. And also it relates the information contained in the 6D partition function to enumerative invariance. Of this threefold. The story is, of course, well known for a long time. In the case where the background is just T2 times Z2 times C2, or also a slightly closely related thing, T2 times tau naught with charge 1. But in this talk today, the relation will be with C2 mod Zn, and its close cousin, the tau naught space of charge n. And in this case, the relation is to the higher rank Donaldson-Thomas theory. On the Calabi-Yau threefold, which is in itself a very interesting topic of ongoing work, and very little is known on how to do explicit computations. And the hope is that by understanding in detail, for example, the modular properties of the partition function, and also just just degrees of freedom of the six-dimensional theory can give some clues on what is a proper way to define and understand this class of invariants, and many phenomena like wall crossing or occurrence of even Mach modularity. So let me give now an outline for the talk. So the strings are instantons, and I will start with a very basic review of instantons and instanton strings when the background is just C2 to warm up. My second step will be to look at instantons on C2 mod Zn. And the third part of the talk will be to understand the role of these chiral fermions that I've already mentioned. So let's start with the simplest, most classical possible version of this story, which is to look at UW instantons in theories with 16 supercharges. Let's look at. Let's try to get a description of the quantum field theory describing a system of k UW instantons. So one way that goes back all the way to the 90s to to understand them is to find a good setup in type 2a string theory or type 2b. So let's look at a system with WD6 branes. Which are described by UW super Yang-Mills theory in 7 dimensions. And let's consider a configuration of K D2 branes. So we can arrange them in the following way. So we have coordinates x0 to x9. And let's take the WD6 branes to be extended along directions 0, 1, 2, 3, 4, 5, and 6. And the KD2 branes to be on directions 0, 1, and 6. So in this case, the coupling in the 7-dimensional theory is between the Ramon-Ramon 3 form. Let's call it B3 and the trace of F wedge F on some 7 manifold, and the D2 branes are just going to be our instantons here. So we can later we want to do something along the 6th direction. So let me just draw the profile of these branes in that direction. It's going to be very simple. Let's see. It's going to be very simple at the moment, but later I will turn it into something more complicated. So we have this stack of KD2 branes, and WD6, and they just fill these directions. If we want to look at the same system along from some transverse directions, we can imagine we have our stack of WD6 branes, and KD2 branes, And the interactions between this system of brains are mediated by strings which are stretching between them. So there are, for example, strings which are stretching between the D2 brains, as well as strings which are stretching between the D2 and the D6. And we can describe this the resulting system living on the D2 brains in terms of a 3D n equal 4 QFT. So from these D2 brains, we get UK gauge group, as well as some adjoint hypermultiplet. And from the D2, D6 brains, one gets an additional hypermultiplet, which is charged under the bifundamental of UK and UW, which from the point of view of the D2 brains is just a global symmetry. Okay, so this is a description of instantons in the 7D Super-Yang-Mills theory. Now let's try to go down to six-dimensional theories. Let's start with theories with 16 supercharges, and let's compactify along x6. So this is x6, and let's shrink the size of this circle to 0. And when we shrink it to 0, it's natural to dualize to type 2B string theory, and we end up with just a collection of D1 and D5 brains extended along directions 0 to 5. And well, the resulting theory in living on the D1 brains is going to be a two-dimensional theory. So we get the 2D theory, and now the amount of supersymmetry is going to be 4, 4, where one can distinguish between left-moving and right-moving supercharges. And the quiver is going to look exactly the same, except now the field content is in terms of representations of 4, 4 algebra in 2 dimensions. And this is, by the way, nothing but the famous ADHM quiver. Yes. Of course. The multiplets follow automatically from the system of brains. So there are strings which mediate interactions between the brains, and they're part of the setup. Yes. So one can, from the ingredients of this brain setup, one can read off automatically the field content. Yes. Thanks for the question. Okay, so we have a two-dimensional Q 4, 4 QFT, which has a moduli space of vacua. In particular, it has a Coulomb branch, which is what I pictured here, where the D2 brains are separated from the D6s. Yeah. Well, you can. Well, in this picture, you can imagine that the D2 brains are separated. They're somewhere at a different point in this direction 7, 8, 9 with respect to the stack of the D6s. But what you can do is you can bring them on top of them, and then you can access. So this first component of the modular space is the Coulomb branch, and there's a second component which is the Higgs branch, which you can access when you bring the D2 brains on top of the D6 brains, and then you can dissolve them and they give rise to instantons on the D6 brains. So really, the physics of the instantons is captured by the Higgs branch of this theory. And indeed, the Higgs branch is just the moduli space of k UW instantons. Okay, so now let's try to get closer to the setup that I'm interested in today. So let's do something different. Instead of putting this sixth direction to be a circle and shrinking it to zero size, let's try to reduce in a different way, which breaks the amount of supersymmetry by half. One way to do it, which is very natural, is to introduce some other branes, which are NS5 branes. And these NS5 branes are going to be extended along the first 6 directions, and they're going to be points on this interval. And this has several effects. So first of all, now we've cut the amount of supersymmetry by a half. So now we are in a situation with 8 supercharges. And we can describe the system effectively in terms of a 6-dimensional theory, which arises from reducing along this interval. So if we take the length of this interval to be L, it turns out the gauge coupling. So in 6D, there's a description in terms of still of UW gauge algebra, and the coupling is going to be, well, 1 over the square of the coupling is going to be identified or proportional to the length of this interval. And now we also started with some collection of D2 branes. Now we're reducing on the interval, and we end up with again some 2-dimensional objects, which are instantons, and they're going to couple to, in the way that we already saw, to the 2-form fields. Now the 2-form fields that arise from the spectrum of NS5 branes. So there's a right one and a left one. With the usual coupling to this instanton term. And on top of that, we have to be a little careful. So one can't just willy-nilly introduce NS5 branes this way. One also needs to make sure that that the brane configuration is consistent. And it turns out that one needs to have also D6 branes which are stretching to the left and to the right of the NS5 branes. And there are more general configurations, but I will just for simplicity consider the case where an equal number of D6 branes is also stretching on the left and on the right. Good. So let me draw down here the resulting 2-dimensional theory. So again, the core piece of the theory is still this ADHM-like quiver. However, one discovers that one needs to also include some additional degrees of freedom, which come from the interactions with these additional stacks of D6 branes. So in particular, these D2 branes can interact with D6 branes on both sides. And this is captured by the fact that there are additional flavor symmetry groups, also of type UW. And these are essential to cancel gauge anomalies of this two-dimensional theory, which now is a 2D n equals 0, 4 theory. So being only supersymmetric on the right moving side, this theory has potential anomalies that need to be taken care of. And the way that it works is exactly by introducing these additional Fermi multiplets that have chiral fermions as their degrees of freedom. Yes, everything is required by consistency, and yes, and yeah. So, well, yes. So if you want, this is kind of a probe approach to see their existence. So already from considering the six-dimensional theory, there are gauge anomalies also in the 6D theory that need to be canceled, and this is only possible if the right matter content of the theory is present. So one can discover them without thinking in terms of these instanton probes. On the other hand, this is another convenient way to discover their existence. And yeah, so there's more than one way to yeah, to save the day if you want to end up with a consistent system. Okay. All right, and now, so now we have a 0,4 theory. Another thing that happened that's interesting is that whereas before we had both a Coulomb branch and a Higgs branch, and we saw that Coulomb branch corresponded to moving the D2 branes away from the D6 branes. Now we've effectively imposed that the D2 branes are terminating on the NS5 branes, so we've pinned them to be on top of the D6 branes, and we've effectively gotten rid of the Coulomb branch. So this 2D 0,4 theory only possesses a Higgs branch, and there's a very interesting story of what happens at the singular point at the origin of the Higgs branch, which corresponds to instantons shrinking to zero size. And it turns out there are some additional degrees of freedom which are localized there. And it's a very interesting story that Kim Young Lee and Juno and So Kim understood in a lot of detail in some similar classes of theories. Okay, so one more generalization before we pass to the case of C2 mod Zn is that now that we have this kind of configuration of branes, there's nothing that prevents us from stacking up additional NS5 branes and continuing this system. So we can do that as many times as we want, actually. And it's convenient to start labeling things now. So there will be a label which runs from 1 to R. Sorry? Here, the separations here are physical scales that correspond to the gauge couplings of gauge groups in 6 dimensions. Yeah, for each one, it's you have an independent parameter. Yes, thanks. So indeed, there's a L1, L2, all the way to LR minus 1. And we can have different numbers of D2 branes. So K1 on this interval, K2 on the second interval, and so on. The only thing I will require is that I don't want to have any D2 branes either on the very left interval or on the very right, because these are infinitely extended, and they would give rise to some degrees of freedom which are infinitely massive. One can consider them as defects and define some defect partition function, but that's like an extra detail I don't want to consider now. Okay, and the story that comes out, well, the quiver that one obtains, it also follows in the same way from this more complicated brain setup. So now we have a multitude of factors of UW, 1, 2, and so on. Actually, ranging from UW0 all the way to UWR, and corresponding to the different numbers of strings, there are different gauge groups. And for each one of these segments, there is a copy of ADHM quantum mechanics corresponding to instantons of the corresponding gauge factor. And the NS5 branes, in the end, can be seen to provide some sort of interface between these ADHM like quivers, with some degrees of freedom that relate the different gauge and global symmetry groups. And yeah. And indeed, all of this follows from just understanding the system of branes, and so. Well, there's quite a lot of additional fermions, right? There are bifundamentals that can. So for each, let's take this one. For each set of D2 branes on an interval, I can have an interaction with a stack of D6 branes on the left, as well as on the right. So these give rise to some additional degrees of freedom that are present because of this interface, if you want, coming from the NS5 brane. Yes. So this is the setup, and one can define now a partition function that basically counts the number of excitations of this type of these type of BPS objects, of these strings, and well, more generally counts BPS states on this background T2 times C2. And it will consist of a perturbative factor, which for today is not so important, but effectively comes from contributions which are purely localized on the NS5 branes and are particles in the six-dimensional theory. And this instanton factor, which is given by a sum of contributions for all possible bound states of D2 branes. So there will be a label, a vector, K, boldface, which takes values in the non-negative integers in R-1 copies corresponding to the different intervals. So this is just the vector of the ranks of the gauge groups K1 to KR-1. And for each such choice, there will be a factor which is this vector of lengths of scales, multiplying K times what's called the elliptic genus with the label W, that tells us about the rank of the gauge symmetry. and k. And this will depend on a number of parameters, such as some holonomies of gauge groups uh, of the various groups of the six-dimensional theory around the two circles of the torus. So I will denote them collectively by zeta, and this also includes the omega background parameters, which have a geometric origin. So they come from the fact that we can actually twist the product between T2 and C2 by using the SO4 rotation group of C2. And that's SU2 times SU2. And as we go around the circles of the torus, we can rotate this copy of C2. And this can be captured by two parameters, epsilon plus and epsilon minus, corresponding to the Cartan of this SU2 times SU2. This is important to regularize the partition function, which otherwise C2 being non-compact would have issues. Okay, so to be more explicit, the elliptic genus is defined as follows. It's a trace with periodic boundary conditions for the fermions of -1 to the f times q to the left moving Hamiltonian, where q is just e to the 2 pi I tau. And there's a q bar to the right moving Hamiltonian. And then we can also keep track of the charges of the various states with respect to the global symmetries of the two-dimensional theory. So there's a collection of abelian currents corresponding to the Cartan of the global symmetry, and this couples to these holonomies zeta. One comment is that this elliptic genus in the omega background, if one turns on all possible holonomies, it's holomorphic, and it's holomorphic because with holonomies turned on, it's the spectrum of the elliptic genus of states of the theory of the 2D theory is discrete, and so it turns out that only states for which the right moving Hamiltonian is 0 contribute to the elliptic genus, and so we have a statement that the elliptic genus is holomorphic. This is not the case, for example, if one considers other backgrounds like Taub-Knot space. Okay. Moreover, one can write down some explicit expression for the elliptic genus, and as an integral over gauge holonomies. So these are associated to the UK gauge groups in 2D, and I will just write it schematically, times a series of the product of one loop factors, which are associated to all the field content of the two-dimensional theory. And this can be written completely explicitly, and the one loop factor is just given by ratios of Jacobi theta functions, which depend on linear combinations of the zetas and tau. And as well as factors of Dedekind eta function. So, so the integrand itself is a Jacobi form, a morphic Jacobi form, and the integral can be performed explicitly, and the final result is that it can be written as a sum over products of Jacobi forms and theta functions, and it turns out to be a weight 0 meromorphic Jacobi form. Okay. So, yes. So there's a prescription which is completely completely non-ambiguous to compute the integral, and it turns out by if one studies localization on the strings that one picks up a series of residues at poles which are determined by a algorithm that follows from the prescription of Jeffrey and Kirwan. So. Residues at values of these gauge holonomies, which are elliptic parameters. So yeah, yes. Yeah, yeah, so this follows from this is a consequence of localization. So one uh, indeed. So these are supersymmetric theories, and one can deform them to go to a limit where only one loop contributions arise in the integral. And this is interesting. So yeah, yeah, and yes, and I want to stress this is this one loop, this localization computation is possible on the world sheet of the string, even if the six-dimensional theory itself is strongly coupled. So this is one of the advantages of looking at these different solitonic sectors. Yeah, thanks. Okay, so now I would like to. Yes, yes. Oh no, it would take me 2 hours. It's a the expressions tend to be quite complicated. Um, I can just say in a few words that the result is a combinatorial sum involving sum over Young diagrams or colored Young diagrams of ratios of theta functions, where the elliptic parameters are combinations of the various holonomies of the various chemical potentials for the system. Sure. Uh, yes. So generally, they have like a high. They have a high number of poles in the denominator. So actually, it's quite cumbersome to split them. But yes, in principle, one can ask what happens if you decompose them into a polar and a finite part. Yeah. So, for example, there's a work of Jeff Harvey and uh, and collaborators on on uh, on elliptic genera of ALE and ALF spaces where they look at this kind of decomposition, and it's closely related. Yeah. Okay, so now let me switch to the background that I'm really interested in for this talk. So far, it was review of results from previous years, and now let's see what happens if we choose our background to be T2 times C2 mod Zn. So again, it's convenient to start with the 16 supercharges in a seven-dimensional theory, and then impose boundary conditions that break the amount of supersymmetry by half and bring us down to 6 dimensions. Also, it's convenient to use a trick that I'm certainly not the first one to use. That's to replace this C2 mod Zn singularity by Taub-Knot space of charge n. So what is this? It's a fibration of a circle over R3. So at the generic point, we have a circle of finite size, and we have a projection onto R3. And this circle can shrink to zero size at some special points known as the centers of Taub-Knot. So tau naught of charge n has n centers, and we can consider some segment which extends from these centers to infinity, and we can look at the inverse of this projection map, and this sweeps out what's called a cigar. So for an interval that ci, the corresponding cigar is script ci. And for tau naught space, the asymptotic size of the circle is finite, whereas if I want to recover the limit of C2 mod Zn, the Ailey limit, then I would want to take this circle to infinity. Okay, so one can consider these cigars for successive centers. So this is for Ci plus 1. And by looking at the differences between these cigars in homology, one can obtain a basis of compact two cycles, which are just taken by gluing these cigars at infinity and then deforming back to some two spheres of finite size. So I will denote these by sigma. Sigma I is Ci plus 1 minus Ci. And they're such that Ci, that sigma I intersected with itself is 2, sorry, it's minus 2, and sigma I with sigma I plus 1 or minus 1 is equal to 1, and all other intersections are 0. So in other words, they intersect like according to the Cartan matrix of type an minus 1. Okay, and moreover, actually, in the type of computations I will do, so what I described here, if you want, corresponds to resolving the singularity. But one can actually turn on a non-trivial B field in string theory on this background, and this allows one to actually bring back all of these poles, all of these centers to be on top of each other and still have smooth physics, even though the underlying geometry is singular. So this is roughly the setup, and now I will discuss the corresponding brane diagram, and the goal will be to determine the theory that lives on the strings. So it's going to be a similar story, but it's going to be a little more complicated. So first of all, I want to do T-duality on the tau naught circle. That will bring me to a configuration in type 2b. And if one performs this T-duality, well, I will draw directions x6 like before, and another direction x5, which parameterizes the dual of the tau naught circle. Okay, and along these directions, there will be a set of NS5 branes. And there will be n of them, and these are effectively what these are what centers of tau naught become upon performing T-duality. Additionally, there will be, originally I had D6 branes. I do T-duality, and I will end up with a collection of D5 branes now. And I need to choose how I want to distribute them with respect to the NS5 branes. So I will break them into collections of, say, little w1, little w, how do I want to do it? Well, let's start little w0, little w1. And actually this direction is periodic, so I will have here a little w n minus 1. I had prepared a specific example, so I want to make a choice. And the constraint is that the sum of w k for k going from 0 to n minus 1 has to be equal to the total rank of the 60 gauge group. Excuse me? Yes, precisely. So in the end, I'm interested in the ALE limit. So where the size of the Taub-Knot circle goes to infinity. So the size of the dual circle should really shrink to 0. So the actual position of the D5 branes doesn't really matter. What matters is the arrangement of the D5s with respect to the NS5s. And in the end, what this is, the data that captures it is just going to be a partition of W. Yes. Yes. Yes, effectively. Yes. So we made contact by taking this background. Now in order to obtain it, to understand the description of the two-dimensional theory, I need to use this trick of switching to ALF space, Taub-Knot space. But from that, I can also backtrack a little bit and understand what happens for ALE space. Yeah. Yes, exactly. So there's So there's a choice of monodromy at infinity for the UW gauge bundle, for the connection of the UW gauge bundle, and I can just consider, I can split it into and look at the Cartan of the gauge bundle, and I can assign a monodromy. So the fact is that that the C2 mod Zn space has a boundary which is non-trivial. This boundary Bn is a length space, which is just S3 modded out by Zn. And this has a non-trivial first homotopy group, which again is a Zn. And I can specify some non-trivial monodromy of the flat connection, of the connections for the Cartan of UW along this circle, with the constraint that if I take n copies of the generator of the homotopy group, I have a contractible circle. So I must have a vanishing flat connection if I take n copies. So the monodromy is, the choice of monodromy needs to be valued in the nth roots of unity. Yes. And these integers, w0 all the way to wn minus 1, are just counting the number of elements of the Cartan which have say monodromy 0, monodromy 1, all the way to n minus 1. So indeed, so this distribution of branes captures the choice of monodromies of the connection, and this becomes a super selection sector for the Right. That's correct. Okay. And okay. And on top of this, now I had a collection of D2 branes, I T-dualized, and now I will end up with a collection of D3 branes, which are going to be suspended between the NS5 branes, and that's effectively how it ends up working. So I can specify a second set of data, V0, D3 branes, which now are literally extended along the horizontal direction and suspended between neighboring NS5 branes. Then V1, V, and -1. And I can consider different choices of different configurations of different numbers of stretched D3 branes. Now there's a few constraints on this. So first of all, inserting the D3 branes is going to affect the Chern classes of the gauge bundle on the D6 branes. So in particular, the integral of the second Chern class turns out to be equal to V naught plus some combination of the WJs. So in particular, this tells you what is the instanton number corresponding to this configuration of these three branes, and it's specified by a choice of this of V0. So a choice of number of these three branes associated to a specific pair of NS5 branes. And on top of this, one can also specify the first Chern class of the bundle. So to specify this, it's convenient to use the fact that there exists a set of line bundles on C2 mod Zn. So R1 to Rn minus 1. Which are the Poincaré duals, whose first Chern class is a Poincaré dual to the two cycles sigma that I drew earlier. So and so this is actually provides the basis of the second cohomology on C2 mod Zk. And so one can expand the first Chern class of our gauge bundle in terms of a linear combination of these with some integer coefficients. Well, or actually fractional coefficients. And now, what's the relation with these multiplicities of D3 branes? That turns out to be quite simple. It's just that Uj is going to be equal to Wj minus the affine Cartan matrix of An minus 1 times this vector of multiplicities V. And then I just look at the J component. So this is the way to map between the data of this brane setup and the data associated to the gauge theory on C2 mod Zn background. And okay, so we're almost there now. So far we are in the setup with 16 supercharges, and now we introduce the boundary conditions, and we go down to 6-dimensional theory with 8 supercharges. So we do this exactly in the same way as we did before. So we introduced some transverse NS5 branes, which now are going to be extended along the X5 direction and are going to cut this brane diagram into different regions. Okay, and again, I don't want to have any D3 branes on the semi-infinite ends of this diagram, but I can have different numbers of D3 branes on the interior with some constraints. And another subtlety is that the numbers of D5 branes, which are suspended on individual segments, can jump in a controlled way. So this gives rise to quite a rich setup. And the way that they can jump is controlled by a subtlety that I haven't mentioned yet. That whereas naively I would expect that I have a UW symmetry for it, which is independent for each one of these segments. In reality, it turns out that of the abelian U1 factor of each one of these UWs, only the diagonal component survives. All the other ones are removed by a Stuckelberg mechanism, which is effectively telling us that they get a mass. It's an analog of Higgs mechanism. So really, there's a overall U1 factor and SUW factors for each one of these intervals. Because there's just a single U1, that's common to all of them. It means that the first Chern class of each one of these bundles must be the same. And that puts very strong constraints on the type of brane configurations, of multiplicities which are allowed. So okay, yes, I will add a label for that as well. So we had this, we had a set of red NS5 branes, if you want, n of them that came from Taub-Knot space. But we also want to have an additional set of NS5 branes here. And I want to have a R of them. So just as in the previous example, this is part of the definition of the six-dimensional theory. It's a rank R theory, so I need R NS5 branes. And now I can try to play the same kind of game and understand what is the theory that lives on the strings. And not too surprisingly, for each one of these intervals, I will get a copy of what's known as the Kronheimer-Nakajima theory, Kronheimer-Nakajima quiver, which has n different nodes with a gauge group which is U Vn minus 1, UV0, V1, and so on, and some global symmetries which are determined in terms of these coefficients W1, W0, etc. So this is for one interval, and if I forgot about everything else, this would be a three-dimensional n equal 4 theory with associated to Kronheimer-Nakajima quiver, which famously captures the instantons of UW gauge theory on C2 mod Zn. But now we we have interfaces between them, and we need to take into account additional degrees of freedom. So now we can add a label to distinguish between the different segments. And so on. And we need to account for all possible interactions, and there's quite a lot of them. So there are some fermionic degrees of freedom that connect the different nodes. For example, this node and this global symmetry node, but also this, and there are some twisted multiplets which connect this. And frankly, it's quite a mess. And one can check if this theory is consistent or not. So one checks for anomalies for the U V A J gauge symmetry groups in 2D. So this has a factor SU, which is anomaly free. But it also has a factor U1 AJ. And this turns out to still have an anomaly, so we're still missing something. And now we discover that there are some additional degrees of freedom in the system that we haven't yet taken properly into consideration. And the reason we didn't is that we've been considering the degrees of freedom coming from the D3 branes, but we forgot to look elsewhere. So this connects to the story of intersecting branes that's been considered in a very nice paper of Seiberg and Isaacson. Well, they looked at the dual setup, but effectively the physics that's described is the same. So I will describe it in our setup. So if we have a NS5 brane, well, if we have two sets of NS5 branes, one vertical one and a collection of horizontal ones that intersect each other, there are some degrees of freedom which are localized at the intersection. So in this setup, the intersection is two-dimensional, and I take it to be our torus. And effectively, from some D strings, D1 branes which are ending on the two NS5 branes, one discovers that there are some fermionic degrees of freedom that are living purely on this torus. So these give rise to additional degrees of freedom on the torus that can couple to the strings. Now, this setup is for Taubnat, and a collection of n complex fermions gives rise to UN current algebra at level 1. Now, it takes a little bit more to see what happens if now we want to pass from Taubnat space to C2 mod Zn. But the answer turns out to be that we can take the SUN subalgebra of UN at level 1. There would be also this additional factor of U1 at level n, but this gets replaced by a copy of the Heisenberg algebra of a single non-compact boson. And these are exactly the right degrees of freedom which are needed to cancel the remaining gauge anomalies of the theory on the strings. Now, this is interesting because, well, for a couple of reasons, but well, the main reason that's also relevant to this workshop is that SUN at level 1 doesn't have a partition function. It has a collection of characters that transform among each other under modular transformation. So because of the coupling to these additional degrees of freedom, the strings themselves are no longer going to possess a well-defined partition function. They will possess a partition vector, or rather a partition tensor, because for each of these NS5 branes, I will get a vector of characters. Now I can write the elliptic genus with this added type of degrees of freedom for this setup. So now I have quite a lot more data. I have for each interval I have a vector of integers w, and I have a vector of integers v's, counting the ranks of the gauge groups. And then I also have a choice of integrable highest weight representations for each one of these current algebras SUN. So let me put it here. There's a W1. So sorry, these range for all the way to R minus 1. And these will range all the way to R. And this I can write now as an integral, like before. Of a big one loop factor coming from all of the contributions from the degrees of freedom coming from the D3 branes. And then I will have the contribution from this additional current algebra. So there's going to be a product of SUN level 1 characters with some chemical potentials that that are going to be linear combinations of these gauge holonomies and other stuff. And this is exactly what's needed to a consequence of the fact that there's an interaction. So I'm canceling gauge anomalies by gauging these SUN currents. And then there will be some contributions from the Heisenberg algebra, which is just factors of the eta function. And so with all this, we end up with an elliptic genus, which in the end can be, again, surprisingly, we computed exactly. So this integral can be performed exactly. It's a complicated expression in terms of combinatorics of colored Young diagrams and so on. But yeah, or rather, I'm using some tricks, some known facts about this kind of integrals to reduce it to a combinatorial sum. So I'm cheating a little bit because JK residues are it's quite a tricky business to compute. But anyways, the final result is that this complicated elliptic genus is now vector valued. Jacobi form, which is meromorphic, just like before. And moreover, the modular transformation properties are completely determined. They follow from the modular transformation properties of the characters of SUN at level 1. And just to summarize what we found, so by itself, the degrees of freedom of the string would want to give rise to a well-defined partition function. But in order to cure gauge anomalies, I need to add interactions with these chiral fermions, which by themselves are not described by a well-defined 2D QFT. They're defined by a relative QFT. One can view them as some boundary QFT for a three-dimensional Chern-Simons theory. And so instantons on C2 mod ZK background are described by relative quantum field theories, and their properties can be understood, at least in this case, in complete detail. And now the hope is that one can also expand the story to other classes of six-dimensional theories where one can exploit the modular properties to determine the elliptic genera and not the other way around. And finally, just one word, I used as a tool the trading the C2 for mod ZN for tau naught space. In the end, I didn't say much about the partition function on tau naught because it turns out it's quite a lot more complicated. First of all, if one has a partition function on tau naught, one needs to account for the possibility of the D3 branes also ending on D5 branes, and that introduces boundary conditions of NUM type. The description in terms of gauge linear of a quantum field theory is no longer something one can hope for. Rather, one should imagine one can imagine there will be a description in terms of nonlinear sigma model, and quite a lot can be said about that. But it's a work in progress. And one of the subtleties is that there will be a continuous spectrum of excitations, and with that comes Mach modularity and wall crossing and all of that. So I will end with this. Thank you. Thanks. Yeah. Yeah, so that's a work in progress with my student Daniele Ceppi. Yeah, it works out very, very naturally. The only subtlety is doing the localization computation, because you can't turn on all the holonomies you would like to be able to turn on, and so that becomes a lot more tricky. Also, enumerating the residues is more complicated business, but that's a technicality. Apart from that, it works out very much the same way. Yeah, yeah, indeed. Yeah. Yes. I have nothing to say about that, unfortunately. No. Sorry. Yeah, okay. Sorry, I forgot to mention that. But at the very end, it turns out that the first Chern classes are completely fixed for these 60 gauge algebras. So it boils down to a sum over the possible instanton numbers. So for each 60 gauge algebra, you end up with a single integer that you need to sum over that counts the instanton number. Now it's fractional, but anyways, it's a discrete parameter. One sums over, and the rest of the data that appears here is the monodromies of the gauge groups that are written here, and also these additional parameters, which I didn't say, but these come from monodromies associated to the two form fields localized on the NS5 branes. So, yes, exactly. Yeah, yeah. And an interesting question is what happens if you, instead of having this simple theory with UW gauge groups, you start with a more complicated six-dimensional theory. So there's, for example, you can start with you can obtain this theory by taking a tau naught W singularity and probing it with a single M5 brane. You could choose a different type of singularity and probe it with an M5 brane to get some interacting 6D superconformal theory. But what happens there is that the M5 brane splits into fractional M5 branes. Those will replace these NS5 branes. And now the question is, what kind of degrees of freedom are supported at these intersections? And that's an interesting question that I wish I knew the answer to. Thanks a lot.